My name is James McLeod. For the AERO4842 design project, I have designed, built, and experimentally tested a prototype Saturnian Dust Measurement Probe, capable of measuring space dust mass and velocity. In this video presentation, I will cover the design of the prototype, sensors used, as well as the relevant signal processing. Finally, I'll perform a live demonstration illustrating the sensor's ability to measure particle mass and velocity. To jump ahead to the experimental demos, just jump to 14 minutes and 15 seconds. So why do we care about Saturnian dust particles? Well, although their exact origin remains uncertain, it is widely believed that the rings we see today are the remnants of an ancient Saturnian moon system. Locked within Saturn's rings are clues not only to their own origins, but also to the broader principles of planetary formation and the complex resonances that govern moon and orbital dynamics. The objective is to develop a sensor capable of measuring the mass, velocity, and kinetic energy of particles within Saturn's rings. These measurements will provide critical data on the ring's composition and dynamics, thereby contributing to a deeper understanding of their origin and of the fundamental mechanisms which govern planetary and satellite formation within the solar system. So let's talk about the sensor and its design at a high level. The sensor was designed to be attached to a probe that is flying through space and would interact with dust particles. Dust particles would pass through the top of the probe, and they would first interact the laser line at the top. So this laser line is shooting a laser across the entire detection area, and it's shooting across to a series of photodiodes on the opposite side of the wall. When a particle passes and breaks that laser beam up, the photodiodes measure that change of incident light as a drop in current. I then pass that current through a transimpedance amplifier, which converts it to a voltage, and then I read that voltage after going through a low-pass RC circuit to my Arduino Uno R4 Minima microcontroller. And based on the drop in voltage, I'm able to know that there is a particle there at a certain time. Then the particle continues in its free fall towards the base. Once it strikes the base, it interacts with the piezoelectric module, and I'm using a piezoelectric disc. When the particle impacts this disc, it induces mechanical stress, and this stress by the piezoelectric effect causes a voltage that I can then measure, sample and measure. So I take this voltage and I pass it through a filtering circuit, an RC circuit, and I sample it at 35 kilohertz. Locked within this voltage is the impulse and the kinetic energy of the particle. So to recap, the particle passes through the detection chamber. It triggers the laser beam break via the response characterized by the photodiode and the transimpedance amplifiers. And then a short time later, it impacts the piezoelectric sensor, where I'm able to measure the voltage induced by that impact. Using those measurements, I'm able to decouple particle mass and velocity from the measured kinetic energy and momentum. So now breaking things down into specific components. Let's first look at the photodiode and laser beam break system. So again, photodiodes just produce a current that is proportional to the number of photons absorbed, and then a particle breaking the beam will cause the current to drop. Current drop is then translated into a change of voltage using a transimpedance amplifier. So I decided to use the Opt11 photodiode as it comes with the transimpedance amplifier already built into a really compact area. So it allowed me to quite easily put it on the breadboard and put that in the detection chamber without taking up too much room. I also selected for this because its peak spectral sensitivity to light is 850 nanometers, and I'm using a red laser at 650 nanometers, which is about 75% of that peak. So we're operating near the optimized range of this photodiode. On the right is the transimpedance amplifier, which is already built in, and you'll see that there is an output, a pin 5. This is the analog voltage, and it feeds back in through pin 4 through off-the-shelf resistor and capacitor, a sign of an RC filter. So what I've done is, instead of using those resistors and amplifiers, because the time constant was way too high, I constructed my own circuit and kind of shorted that output and rerouted it to pin number 2, which is at the top, and it allowed me to design my own RC time constant. And so I selected that time constant to be about 25 microseconds to allow me to detect particle passing events when they would only be covering the photodiodes for a matter of microseconds. And this is what the photodiode triggering looks like when I dropped a 2 millimeter salt particle from about 10 centimeters above it. So we can see that the RC constant allows the circuit to be quick enough to actually detect these impacts, just the particles passing. So we see a spike in current or voltage followed by a drop. So I'm able to detect this and know the time of particle passing at this point in space. The next step was the piezoelectric material at the base. So I selected a piezoelectric disc with a relatively low natural frequency. I needed this natural frequency to be low since I'm sampling the signal at about 35 kilohertz, and based on the Nyquist sampling rule, I needed that signal which I was sampling to be no greater than, say, 16 kilohertz. So the sensor, or the piezoelectric disc that I selected, had a natural frequency of about 1.6 kilohertz, so I was well within that Nyquist threshold. And so piezoelectric materials produce a voltage under applied mechanical stress due to separation of charges in the crystal structure. And so upon impact with a particle, that stress creates voltage, and the sensor resonates at its natural frequency. And so it ends up looking like a damped harmonic oscillator in terms of the voltage response. Once I obtain the voltage, I'm able to turn that, using some correlations, into particle kinetic energy and momentum. So to actually get that voltage, I designed the following piezoelectric circuit. So there are a couple of key elements that went into this design process. First, I needed to bias the voltage to plus 2.5 volts, since the piezoelectric material will oscillate into the positive and negative regimes, and the Arduino can only read positive voltages. I needed to clamp it to 0 and 5 volt rails to protect the Arduino inputs. And then I again selected another RC circuit, time constant, such that the 3 dB cutoff frequency would be well above the frequency of the piezo, so I wasn't filtering it before I even read it with my Arduino analog to digital. And now with those measurements, I was able to calculate the particle velocity. So in a weightless environment on orbit, it would simply just be the change in distance over the change of time, assuming, since the change of distance is so small, that the velocity is constant. But testing on Earth, we're subject to Earth gravity, and so I just do a simple Earth gravity model here without any air resistance, because the particles are traveling relatively slow and with a relatively high mass to surface area ratio that it's negligible. And the next thing I needed to measure was the kinetic energy. So I did this by building a linear correlation between particle energy and the measured peak voltage on the piezoelectric sensor. So I did this by selecting several masses and dropping them from known heights to create a known velocity and thus a known particle energy. With those known energies, I then recorded the maximum voltage, and over 20 trials I built a linear calibration. So this allows me then to take unknown particles, drop them, and back calculate from the voltage what the kinetic energy is. Another thing I measured was particle momentum. The way I did this was by first obtaining that voltage signal from the piezoelectric sensor upon impact. I then reconstructed the force response that the particle imparted onto the piezo sensor. And I did this in the frequency domain by deconvoluting the force signal, which was measured, from the impulse response of the piezo. And so I modeled the piezo as a second order damped harmonic oscillator, which meant I needed to characterize the damping ratio and natural frequency, which is detailed in the report, but I was able to do that empirically. So now I've obtained the force signal, and assuming that all of the particle momentum is lost through the impulse of that impact, we can then equate the total momentum to be the integral of the force signal over the impact time. So at this point now I've calculated particle kinetic energy as well as particle momentum, and by dividing and doing some operations with the known velocity that was also calculated, we have two methods of obtaining the particle mass. So here's some experimental results. These three plots basically characterize the piezoelectric response. So on the left is the raw voltage response, and we see it's behaving just like a damped harmonic oscillator with the exponential envelope squishing that sine wave down. Next, we have the reconstructed force signal, which is obtained through deconvolution of that voltage and the impulse response. And then on the right is the FFT spectrum of the voltage signal. So the key things to note here is that this clearly shows that the sampling
frequency that I'm using, which is 35 kilohertz, is above and beyond the Nyquist frequency, since I'm able to adequately characterize the voltage signal. I'm also smoothing the force signal after the deconvolution just to eliminate noise when I end up calculating the momentum. And the FFT spectrum gives us the peak frequency about 1.6 kilohertz, and it indicates there's only really one peak here, so we're really operating that single mode of vibration. And so we have some results. So this is just the graph from earlier. I just wanted to reiterate, this is for a calibrated range. So I've calibrated up to masses up to 4 grams, or 0.04 grams. So the first set of results are from within the calibrated range. So I took a 0.2 gram particle and I dropped it from 14 centimeters above the piezoelectric disc. And I recorded the corresponding mass and velocity estimates based off of that. So on the left are the velocity measurements. The error bars on both plots were calculated through an extensive error propagation using a Gaussian uncertainty model. And so these error bars correspond to 1 sigma of that measurement uncertainty. For full details regarding all of the measurement uncertainties, such as the measurement voltage error, the measurement damping ratio, measured natural frequency, measurements in terms of the transient timings calculated for the velocity, all of those uncertainties were propagated in to calculate those error bars, and those details are in the report. But anyways, on the left-hand side is the velocity. And so the expected velocity was about 1.66 meters per second, and over 5 trials, the average was about 1.63 meters per second, showing that this sensor is capable to, within about 5 centimeters per second, calculate or measure the actual particle velocity. On the right-hand side are the mass measurements, and I introduced 2 methods of calculating mass. One was from the linear calibration, or the energy method, and the other was from the convolution of the impulse response, and so that's the momentum method. We can see here that the mass from energy method is much closer to the target mass, and it's about a 5% deviation when we're operating within that linear calibration range. The triangles on that plot correspond to the mass from momentum, and the error here shoots up about 100 and 200% off of the expected value. So this indicates a fundamental error with how the piezoelectric is being modeled in terms of the impulse response, since the voltage was deconvoluted using that impulse response. Again, I was just modeling it as a single degree of freedom damped harmonic oscillator, so better results may be achieved through a more extensive modeling of that piezoelectric disc. So in conclusion, for the results inside the calibrated range, I'm able to adequately measure the velocity and the mass using one method but not the other. But then we move outside of the calibrated range, and again the velocities are still within about 5 centimeters per second of the target, or the known velocity. In this case it was 1.9 meters per second. So I took a heavier mass here and I dropped it from higher, using a mass of about 0.05 grams, so moving outside of that linear calibration range. And the key plot where this has an effect is on the measured mass. This is expected because the velocity is completely independent of the mass, so it's a completely independent measurement. The mass, however, the circle points there indicate to that mass from energy method using the linear calibration. Clearly, once we step outside of the linearly calibrated range, then that measurement falls off, and so there's an error right here of about 80%. The mass from momentum, again, is about another 50% error, so is even outside of a calibrated range for any of those mass determination methods, it's not robust. So this demonstrates that for the sensor to be effective in an on-orbit scenario, it needs to be operating in a calibrated range. Now it's time for a live demo. And so now I'll perform the demonstration. So as there's no impact, MATLAB is not receiving any data. So I'll take a known particle of mass of 0.01 grams here, and I'll drop it from precisely 14 centimeters above the unit. It passes through the beam, it hits the sensor, and then MATLAB plots the live results. So the uncropped screen recording here will just show those plots updating in real time, as well as the mass, energy, momentum estimates being calculated and output live to the user. And so that last test was with a relatively light object within the calibration range. Next, I'm going to take a substantially heavier object and perform the test again. So we'll take our object. This time we'll drop it from a higher height right in there. And the MATLAB plots are live again. So those two videos give an idea of how the sensor works. It detects particles, it measures the mass and velocity, and in real time the Arduino is communicating with MATLAB to perform those calculations, produce those visualizations, as well as tell the user at that instant what the measurements are. So in the future, this would have been implemented more with like an SD card on the spacecraft. And so it would have been saving all of that data to a flight computer and getting it ready to transmit back to Earth. In conclusion, this project has successfully integrated photodiode sensors, transimpedance amplifiers, low-pass RC filtering circuits, piezoelectric sensors, high sampling rates via the Arduino MCU, communication between the Arduino microcontroller and MATLAB, and then subsequent signal processing and data analysis within MATLAB. The result is a prototype space dust measurement sensor, which has been demonstrated to measure millimeter-sized particles traveling up to 2 meters per second. So in this presentation, we've talked about the technology involved and a couple of live demonstrations. Further details regarding how this would perform in the space environment and improvements that would be needed to be made are included in detailed discussion in the report. But thank you for watching this presentation. I hope you enjoyed. If you have any questions about this or any of the contents within the report, please feel free to reach me by email. Thank you.